Hi, good morning, one and all. Hi, I'm Vishal. I'm from Triple Engineering, third year. So I'm here to explain about memory-based event triggering load frequency control for power system. So here, modern power systems are typical networked control systems in which the power plants, sensors, and the control center are connected through wide area communication infrastructures. For power systems, the load frequency control LFC is widely used to stifle the fluctuation of frequency caused by load disturbances. Recently, electric vehicles (EVs) can reduce greenhouse gas emissions and minimize their dependency on fossil fuels. The problems of EVs incorporating the LFC have been investigated in a lot of literature. For example, by designing a proper feedback controller with the help of incorporation of EVs, LFC can maintain the frequency at an expected value and make the entire power system stable. However, disturbed by the wireless communication network environment, the power system have some inevitable challenges such as time varying, network delay, packet losses, or cyber attacks. More recently, a great deal of pioneer researchers have paid attention to these problems. So here, to overcome the shortcoming of the time triggered scheme, much attention has been paid to the event triggered scheme (ETS) in the past two decades, and the references therein among them. Many popular ETSs have been proposed. For example, the continuous ETS, mixed ETS, dynamic ETS, discrete ETS, adaptive ETS, distributed ETS, and so on, to a name few. In order to avoid a Zeno phenomenon, Hummels and Zhao et al. Strike a balance between the time-triggered scheme and continuous ETS and proposed a periodic discrete ETS for linear systems. Based on this works, an adaptive ETS is developed in the 24 and 34, wherein the triggering parameter can be adjusted adaptively according to the system dynamics. So here the structure of the dynamic model of a power system is illustrated, wherein the EVs participate in the LFC scheme in both the secondary frequency control and primary frequency control of the power system. The system model is represented as follows: x of t is equals to a of x of t minus b into u of t plus w of t into y of t is equals to Cx of Tkh, where x of t belongs to R5, u of t belongs to R, w of t belongs to R. So y of t belongs to R to R respectively. The state vector, control input, disturbance, and measurement output. H is the sampling period. Tk are integers, and t0 and t1 belongs to 0 and tkh denotes the released sequence of the sampling instance. The state and measured output signals are xt of t is equals to f of t into x of g of t, pg of t, pe of t, yt of t is equals to f of t. So here we can see in this diagram, we can see the parts METC Q buffer 1 networks connected to controller and connected to Q buffer. So here controller connected to AG and AE and connected to networks. Networks are connected to summing points, where summing points are connected to the electric vehicles 1 by 1 plus STG XG 1 by 1 plus ST1 1 by 1 plus STC 1 by MS plus D. Diagram of it is a diagram of event triggered power systems under deception attacks. So memory based event triggered scheme. In this part, we first review that the periodic ETS proposed is 36 Tk plus 1H is equals to Tkh plus minimum I belongs to N, where I belongs to N, satisfying IO in such a way many redundant sample signals are dropped. Thus, the bandwidth of the network channel can be saved and the computation burden of the controller is mitigated. So it should be pointed out that up to now most of the ETS in the published references only consider the current sampled data TKL of H or X of T and the most recent released signal X of TKH. However, some recently released released package still contains some useful information on in determining the extra possible released signal to illustrate the positive effect of the historic released signals. A simple case is illustrated before that an index lambda t k minus 1 plus L is defined to demonstrate whether whether a new sampled signal deserves to be transmitted or not. Here we can see that the index lambda tk minus 1 plus L is defined to demonstrate. It is defined further to demonstrate the whether new sample signals are transmitted or not. It defines that thing. So in the existing ETSs, only the newly sampled data and the recently released signals are used in the event generator. However, at the cluster trough of this trough of the state output is curve such as x of t of 4 of h dx t5h, the error between two adjacent samples may be very small, which is easy to drop by some existing ETSs. However, the values of these packets are usually much larger than others at an instance, and the controller needs more packets such as that more control effort can be implemented. However, this cannot be accomplished by the existing ETSs. In the proposed METS past released signal are used. It is easy to see that if m is equals to 1, the METS reduces to the ETS in 2. That is, the ETS in 36 can be seen as a special case of the proposed METS. Totalism, historic signals. A buffer is needed at the event generator site to start the most recent released M packets. The waiting parameters UI are used to demonstrate the importance of the historic released packet, etc. pack. Generally, we guard that new sampled packets are more important than the old ones. In this article, we require that ui is greater than or equal to ui plus 1 is I is equal to 1 to m minus 1. It should be pointed out that when considering randomly occurring deception attacks, if we still use a buffer at the controller side, the faked signal and the unfaked signal will be mixed together, which makes the controller difficult to be designed. To overcome this problem, a new schedule method is proposed to deal with the situation caused by the deception attack. The first, a buffer at the METS side is still needed, which is used to store the released packets y of tk minus ih is equals 0 m to m minus 1, where while instant m stored packets are packed together and sent to the controller. If this packet signal experiences deception attack, the received signals should be y of tkh to fm of y of tk minus m plus 1h, else the two signals y will be received by the controller. In order to demonstrate the effectiveness of proposed METS under deception attacks, two cases are proposed. In case 1, it is assumed that the number deception attacks are considered. Through case 1, it can be concluded that compared with ETS in the proposed METS constabulary steps. So here we can see the graphs. In first graph, So in first graph it is increasing, it is constant. In second graph it is slowly decreasing to increasing and becomes constant. It is a result of case 1 and say results of case 2. State response constant and result release intervals with MN. And thank you so much.